Hello my friends and welcome to my channel. Walter here, and today I'll be taking you through the October-November 2023 Further Pure Maths 1 paper, that's 9231/11. Now I hope you're gonna learn a lot from what we're gonna be discussing in this video, so let's get started. Alright, so we're starting with question number 1. It says, by considering r plus 1 squared minus r squared, use the method of differences to prove that the sum to n of terms of the form r is equal to half n of n plus 1. Alright, so let's work this question out. Here, they want us to make use of r plus 1 squared minus r squared. So I'll say the sum from r is equal to 1 up to n of r plus 1 squared minus r squared should give us, when r is 1, we'll be having 1 plus 1 squared minus 1 squared, which is 2 squared minus 1 squared. When r is 2, we will be having 3 squared minus 2 squared. When r is 3, that will be 4 squared minus 3 squared, and so on. And term that comes before the last, that is the term when r is equal to n minus 1. So when r is equal to n minus 1, we'll be having here n minus 1 plus 1, which is n squared, minus n minus 1 squared. And the last term, finally, that's when r is equal to n, it will be n plus 1 squared minus n squared. Right, so for the terms in this series, you can see that if we add these two terms, they give us 0. 2 squared minus 2 squared is 0. 3 squared minus 3 squared gives us 0. So this term will also be eliminated along the way. And so does n squared minus n squared give us 0. You can also see that n minus 1 squared will be eliminated along the way. So basically, we will be left with minus 1 squared plus n plus 1 squared. So that's the sum of terms of the form r plus 1 squared minus r squared. Now, you have to understand that when we say the sum from r is equal to 1 up to n of r plus 1 squared minus r squared, it is the same as saying the sum from r is equal to 1 up to n of, and expanding the brackets here, we get r squared plus 2r plus 1, and that's minus r squared. Now r squared minus r squared is 0, so we are left with 2r plus 1. So basically, this is the same as the sum from r is equal to 1 up to n of 2r plus 1, which is the same as 2 times the sum to n of r plus the sum from r is equal to 1 up to n of 1. And this is the same thing which we got to be giving us this result. So all this is equal to minus 1 squared, which is just minus 1, and it's plus n plus 1 squared. So this is what we're getting right here. All right. Now we can simplify what we have. So we can say here 2 times the sum from r is equal to 1 up to n of terms of the form r plus this here gives us n times 1, okay, which basically is n. So that's all equal to minus 1 plus n plus 1 squared. I'm going to take n to the right side, okay, and if we do, that will be 2 of the sum to n of terms of the form r is equal to n goes to the other side and becomes a minus n. So it's minus n minus 1 plus n plus 1 squared. Now I'm going to divide both sides by 2. So we'll be having the sum from r is equal to 1 up to n of terms of the form r being equal to a half, right? And it's a half of, here I'm going to factor out minus 1. So it's as good as we have minus of n plus 1, and it's plus n plus 1 squared. So this is what we got right here. Now I'm going to simplify what we have inside the square bracket. So I have a half outside, and inside the square bracket, what I'm going to do is I'm going to factorize, so factor out n plus 1. So I have n plus 1 here, so close bracket, and dividing n plus 1 into minus of n plus 1, we get minus 1, and dividing n plus 1 into n plus 1 squared, we get remaining n plus 1, close bracket, like this. So essentially what we have is a half, and here minus 1 plus 1 is actually 0, so we're left with an n, so n, and that's of the n plus 1 that we already have right here. So what we have now is the final answer. Okay, so going back, you can see that the question actually wanted us to show that the sum to n of terms of the form R is half n of n plus 1, and that is actually what we got right here. All right, so we're saying therefore the sum from R is equal to 1 up to n of terms of the form R is half n of n plus 1, therefore shown or proved. Okay, so we're done with this part. Let's go on to part B. Part B says, given that the sum to n of terms of the form R plus A is equal to n, find A in terms of n. Right, so we are saying here the sum from R is equal to 1 up to n of R plus A is equal to n. That's what they're saying here. All right, so we are saying that it's like the sum from R is equal to 1 up to n of R plus the sum from R is equal to 1 up to n of A being equal to n. All right, now we got the result for sum to n of terms of the form R to be half n of n plus 1, right? And it's plus here. We know that this gives us n times A, since A is a constant, right? So basically that's an is equal to n. So this is what we are having right here, right? So let's simplify it. They want us to make A the subject. Okay, they say we should find A in terms of n, so that's what we seek to do here. So I am going to rearrange so that I'll be having on the left hand side an being equal to, and I'll take the half n of n plus 1 to the right side, so we'll be having n minus half n of n plus 1. So we can simplify what we have on the right hand side. So that's n minus half n squared, and it's minus a half of n, which can also be simplified to give us, here we can say n minus half n is half n. So we have half n minus half n squared. All right, and I'm going to factor out a half n here, so that we'll be having 1 minus n left inside here. So if we divide both sides by n, we will be left with A being equal to a half of 1 minus n. And what we have right now is the answer. All right, the question was saying we should find A in terms of n, and that's what we got right here. So let's move on. Now we are on question number 2, which you can see right here. They say we should prove by mathematical induction that for all positive integers n, the series given here is equal to this, right? So basically they want us to prove by mathematical induction. All right, so let's do that. All right, so we're going to start by proving for n is equal to 1. So when n is equal to 1, the left hand side will be such that we will only be talking about the first term. Remember, n gives us like the number of terms, like which term it is. So when we say n is equal to 1, we only mean the first term in this series. So the left hand side is equal to 1. the right hand side will be 1 minus 1 plus 1, which is 2x to the 1 plus 1x to the, so that's going to be x squared, and that's going to be over 1 minus x squared. All right. Now, this is the same as, if you can see, 1 minus 2x plus x squared is actually a perfect square. It actually is 1 minus x squared when factorized. So it's over 1 minus x all squared, and when these two divide each other, we get 1. So therefore, we are saying that the statement is true for n is equal to 1. Let's move on to the next part of our proving. We are going to assume, assume true for n is equal to k. So what we're saying here is the summation 1 plus 2x plus 3x squared all the way up to, now n is k, so that's k, x to the k minus 1 should be equal to 1 minus k plus 1, all right, of x to the k plus k x to the k plus 1, and that's all over 1 minus x squared. So this is what we are assuming is true. All right. Now we prove for n is equal to k plus 1. Now for when n is equal to k plus 1, we are saying that it is the same as the sum to k plus 1. All right. So sum to k plus 1 of terms of the form. Now the form of the terms in this series is going to be rx to the r minus 1. So we have right here rx to the r minus 1. So this is a representation of the series right here, but with n being equal to k plus 1. Right. Now this is going to be the same as the sum from r is equal to 1 up to k plus 1, actually up to k, right, of terms of the form rx to the r minus 1, and plus the k plus 1th term. All right. So I want you to understand what's going on. If you have a series, right, with terms 1, 2, 3, okay, first term, second term, third term, up to the, let's say, the kth term, all right, we know that the k plus 1th term comes after the kth term. So that's the k plus 1th term. So the sum from 1 up to the k plus 1th term, which is what we have right here, is the same as adding the sum to the kth term plus the k plus 1th term itself. So you understand why we are doing that, because we will need to make use of the assumption, okay, our assumption that we got previously. Okay, let's continue. So basically, this is going to be, we know that this from the assumption is equal to 1 minus of k plus 1 of x to the k plus kx to the k plus 1, and this is all over 1 minus x all squared, and it's plus the k plus 1th term. Now the k plus 1th term, remember the form of the terms in this series is r of x to the r minus 1. So we're substituting k plus 1 for r, right? So that's going to be k plus 1 of x to the k plus 1 minus 1, which basically will be to the k. So this is what we'll be having, all right? Now I'm going to say this is all over 1 so that I can combine these two things that we got, right? So we're going to have right here, okay, the common denominator is 1 minus x all squared, and I'll cross multiply. So 1 multiplies this thing on the left side, which is 1 minus of k plus 1 of x to the k plus kx to the k plus 1. And that's going to be plus the product of these two, which is going to be 1 minus x squared of k plus 1 of x to the k. So this is what we have when we combine the two. All right. So let's continue with it. Okay. So we are saying here, we can simplify this a little bit further. I'm going to expand the brackets, all right, all the way through. So here I'll be having 1 minus kx to the k, and it's minus x, actually that's x to the k, yes, and that's going to be plus, here we have the kx to the k plus 1, all right, and here I'm going to expand the last two terms, and that will give us kx to the k plus x to the k, and that's of 1 minus x squared. So that's going to be all over 1 minus x squared. Let's continue simplifying. We'll be having 1 minus kx to the k minus x to the k plus kx to the k plus 1 plus kx to the k plus x to the k, and expanding this bracket we get 1 minus 2x plus x squared all over 1 minus x squared. All right, now we're going to continue expanding the brackets here, so I'll need a bit of space, more space. So I have the 1 minus kx to the k, right, minus x to the k plus kx to the k plus 1, all right, and I'll have right here this term multiply the second bracket, so it will multiply kx to the k times 1 will give us kx to the k, also multiplies this term, and we get minus 2k x to the k, also will multiply the last term, and we will get plus kx to the k plus 2. All right, so that's what we'll be having right there. Next up, we will have x to the k multiply the second bracket, so times this, it will give us x to the k, and we'll also multiply the second one, and we get minus 2x to the k plus 1, and we'll multiply this, and we will get plus x to the k plus 2. So that's what we have right here, and all this is over 1 minus x squared. All right, now for the like terms, okay, simplifying the numerator, we have the 1, and so 1 we have taken it, and minus kx to the k, right, plus kx to the k will give us 0, minus x to the k plus this x to the k also give us 0, right. Then we also have the kx to the k plus 1, right, so I'll just write it as it is. So we have kx to the k plus 1. We also have, okay, so we have taken this term, so good. We also have minus 2x to the k, and I can see that actually it's supposed to be minus 2kx to the k plus 1, because we actually got this particular term when we multiplied kx to the k times minus 2x. So that should give us minus 2kx to the k plus 1. All right, so it's minus 2kx to the k plus 1 we have right here. So I'm gonna put it here, it's minus 2k of x to the k plus 1. All right, then we also have kx to the k plus 2. All right, so it's plus kx to the k plus 2 here, then the minus 2x to the k plus 1, and it's plus x to the k plus 2. O over 1 minus x squared. All right. Now, we can also notice that kx to the k plus 1 minus 2k x to the k plus 1 give us minus k x to the k plus 1. And the rest is plus kx to the k plus 2 minus 2x to the k plus 1 plus x to the k plus 2. And this is O over 1 minus x squared. All right. So what we have here can be simplified to 1. And if we consider this term here and this term here, we can factorize them into minus of k plus 2 of x to the k plus 1. And if you look at this term and this one here, we can factorize them, factoring out the x to the k plus 2, and we get k plus 1 of x to the k plus 2. And this is O over 1 minus x O squared. All right. Now, what we have right here is showing us that the statement is true for n is equal to k plus 1. In the sense that if we substitute n for k plus 1, it will give you back this thing that we have right here. All right. So I will say this is true for n is equal to k plus 1. All right. And then our concluding statement will say, since true for n is equal to 1, and if true for n is equal to k, it is also true as proved for n is equal to k plus 1, and therefore true for all positive integers n. So that's how we do it for this particular question. Let's go on to number 3. On number 3, they say the quadratic equation x to the 4 plus bx cubed plus cx squared plus dx minus 2 equal to 0 has roots alpha, beta, gamma, and delta. It is given that the sum of the roots is equal to 3, sum of squares of the roots is 5, and sum of these terms is equal to 6. So on part A, find the values of B, C, and D. All right. Okay, so I'm going to say 4x to the 4 plus bx cubed plus cx squared plus dx minus 2 equal to 0. What we know is that the sum of the roots is found by minus b over a, which in this case will just be minus b. We know that the sum of product of pairs is c over a. The coefficient of a power 4 is a. So basically that's c. We know that the sum of product of triples, okay, is minus d over a, where a is 1 in this case, so minus d. And we know that the product of roots actually is e over a, which in this case is just minus 2. So this is what we know. All right. Now for our particular case, we have been given that the sum of roots is 3. All right. So basically, it means that the sum of roots, which we represent by minus b, is 3, which leads us therefore to having b to be minus 3. So this here is the first value that we have obtained. All right. Next up, we have been given that the sum of squares is 5. Now, the sum of squares of the roots is found by the sum of the roots squared minus 2 times the sum of product of pairs. Now the sum of roots is minus 3, is actually 3, so 3 squared minus 2 times the sum of product of pairs. The sum of product of pairs is c, so it's minus 2c. All right, and the sum of squares, they've given us that it's 5. Okay, so we need to solve for c here. So 2c will be 9 minus 5, which is 4, which gives us c to be 2 here. So c is 2 right here. Okay, next up, they've told us that the sum of these roots, okay, the reciprocals of the roots, is equal to 6. All right, now this, which is the sum to the minus 1 plus this plus this plus this equal to 6, is the same as 1 over alpha plus 1 over beta plus 1 over gamma plus 1 over delta is equal to 6, is the same as the sum of product of triples, okay, over the product of roots. That's what this actually represents. All right, if you combine this 3 into 1. All right, so the sum of product of triples is minus d over the product of roots, which we got to be minus 2. All this is equal to 6, which therefore leads us to having d coming out as 12. So we have d to be 12. So that's how we answer this question here, part A. Let's move on to B. On B, they say that given also that the sum of cubes of the roots is equal to minus 27, find also the value of this. All right, so for this we are going to take the original equation here. So basically we have x to the power of 4 plus bx cubed plus cx squared plus dx minus 2 being equal to 0. And remember, we got the values of b, c, and d. So it's h to the power of 4, and we got b to be minus 3. So it's minus 3x cubed, and we got c to be 2. So it's plus 2x squared, and we got d to be 12. So it's plus 12x minus 2 equal to 0. I'm going to make x to the power of 4 subject. So this is the same as x to the power of 4 being equal to 3x cubed minus 2x squared minus 12x plus 2. All right. Now, since alpha, beta, gamma, and delta are roots, we can substitute alpha, beta, gamma, and delta into this equation. And if we add up these terms, we will get the sum of roots of terms of the form alpha to the 4. And adding up these, we will get the sum of terms of this form, actually 3 times. And here, we will get 2 times the sum of terms of the form, this form, alpha squared. And it's minus, adding up these is minus 12 of the sum of the roots. And adding up these, we get 2 times 4, okay, which is 8. So this is what we get. All right, so basically this is alpha to the 4 plus beta to the 4 plus gamma to the 4 plus delta to the 4, and it's equal to 3 times the sum of these roots, okay, of the cubes of roots is minus 27 minus 2 times the sum of squares of the roots. We got that to be 5. So we have 5, and it's minus 12 the sum of roots. The sum of roots is 3. So we will have 3 here, and it's plus 8. All right. So if we calculate this, we will certainly get minus 119 for our answer. So this is the answer we get for this particular question. That's how we do it. Let's move on to number 4. On number 4, they say lines L1 and L2 have equations. R is equal to minus 2i minus 3j minus 5k plus lambda minus 4i plus 3j plus 5k, and R is equal to 2i minus 2j plus 3k plus mu of 2i minus 3j plus k respectively. On part A, find the shortest distance between L1 and L2. Alright. Now, to find the shortest distance between two lines, we use the formula D is equal to the modulus of A1 minus A2 dot B1 cross multiplying B2, and this is O over the modulus of B1 cross B2. So this is the formula we use for shortest distance between two lines. A1 and A2 are the points on the lines, right? So for our A1 minus A2, we are using the points minus 2i minus 3j minus 5k, all right? And that's minus A2, which is this. That's 2i minus 2j plus 3k. All right, so we're subtracting this 2 and we get minus 2 minus 2, that's minus 4i, and minus 3 minus minus 2 is minus j, and minus 5k minus 3k is minus 8k. So this is what we are having for A1 minus A2. Next up, for B1 cross B2, it's like we are finding the vector product of these two, this one here and this one here. So that's minus 4, 3, 5, cross multiplying 2, minus 3, 1. All right. So for this vector product, we should get here, if we close out these, we will get 3 minus 15, and this is going to give us 18. All right, so basically that's 18i. And next I will close these terms, so I'll do minus 4 minus 10, which is minus 14, but I'll also put another minus on there, which will make it positive 14. So I have 14j. All right, and lastly I am going to close out this, and we do 12 minus 6, which is 6. So here we get 6k, like this. So we now have B1 cross B2. All right, we will also need modulus of B1 cross B2, which is like the square root of 18 squared plus 14 squared plus 6 squared. So simplifying this should give us 2 root 139. All right, so therefore D should be equal to, now the dot product for this 2, which is the scalar product, we calculate it as minus 4 minus 1 minus 8, okay, dot, and we have 18, 14, 6, and that's over 2 root 139. All right, and on top, that's gonna be minus 4 times 18 plus minus 1 times 14 plus minus 8 times 6 all over 2 root 139, all under modulus, which should simplify the numerator to minus 134, which is 134 basically under modulus, and it's over 2 root 139. Okay, dividing 2 into 134, we get 67. So basically, the answer is 67 over the square root of 139. So this is what we get right here. Let's go on to part B. On part B, the question says the plane pi contains L1 and the point with position vector minus I, minus 3j, minus 4k. So on part B, find an equation of pi giving your answer in the form ax plus by plus cz equal to d. Alright, so we have here a plane, and this plane contains L1, and it also contains a point with coordinates, actually with position vector this, right? So this is what we have right here. So we're going to need to know what the point on the line is so that we can find the vector. So let's say this point is P. So I'll say P. And the point on L1, let's just call it A. So we will need to find the vector AP, which is OP minus OA. OP is this vector they've given us, minus I, minus 3j, minus 4k, and this minus OA is a point on the line L1, and the point on the line L1 is this one, minus 2i, minus 3j, minus 5k. Alright, so I'll have that. That's minus 2i, minus 3j, and minus 5k. This simplifies to minus 1. Okay, let me just, minus I minus minus 2i is I. And minus 3 minus minus 3j is 0. And then minus 4k minus minus 5k is actually k, so it's plus k. So this is what we're having for AP. All right, so we now have two vector directions. Okay, we have the AP and we also have the direction vector of the line L1. So we can actually do vector product. Okay, vector product of the two vectors, the I plus k vector we've gotten, and vector product with the direction vector of L1. The direction vector of L1 is minus 4i plus 3j plus 5k. Okay, so with that, that's minus 4i plus 3j plus 5k. And this will give us the normal to the plane. Okay, this will give us the normal to the plane, and the normal to the plane is perpendicular to the plane. In this it's a perpendicular to these two vectors. All right, so it's a common perpendicular. So for vector product, that's 1, 0, 1, right? And minus 4, 3, 5. So for this, I'll close out here and I'll have 0, minus 3. So minus 3i here. Then next, I'm going to close these and I'll have 5 minus 4, which gives us 9. And I'll put a minus on that. So it's actually minus 9. So minus 9j. And lastly, I'll close these and I'll have 3 minus 0. That will give us 3. So I'll have here plus 3k. So this is what we have right here. All right, so that's the n. Now we also need to find d. D is found by a dot n, which would be the scalar product. So basically minus 3 minus 9, 3 dot product with a, which is a point on the plane, and the point of the plane on the plane we can use either the point P or the point A. Let's use the point P, okay, which has scalars minus 1, minus 3, minus 4. right? So here we will say minus 3 times minus 1, which is 3, plus minus 9 times minus 3, which is 27, and it's plus 3 times minus 4, which is minus 12. So basically we have 3 plus 27 minus 12, which gives us 18. So that's the D right here. So therefore, for the equation of the plane, we will say that it is equal to, in Cartesian form, minus 3x minus 9y plus 3z, alright, and is equal to 18. Now, what we have now can be simplified by dividing by 3. So if we divide each item by 3, we will get the final answer for the equation of the plane in Cartesian form to be minus x minus 3y plus z is equal to 6. So what we have right now is the answer. And that's how we do it. Let's now move on to question number 5. They say, let K be a constant. The matrices A, B, and C are given by A is equal to this, B to this, and C to this. It is given that A is singular. So on A, show that CAB is equal to this. Right? So we are talking about CAB, but before we get CAB, we have to make use of the fact that A is singular. So if A is singular, we can find the determinant of A, and we know that singular matrices have a determinant equal to 0. So for the determinant, I will take 1 and close out, and we get 1, 3, 2, 5. All right. So 1 and 1, 3, 2, 5. Then I'll close out K. So 2, 3, 3, 5. So that's gonna be minus K of 2, 3, 3, 5. Then I'll close out for the 3, 2, 1, 3, 2. So it's plus 3 of 2, 1, 3, 2. So basically this is 1 of 5 minus 6, which is minus 1. And here minus K of 10 minus 9, which is 1. And 3 of 4 minus 3, which is 1. Okay, and all this should be equal to 0 because it's a singular matrix. So basically we have minus 1 minus K plus 3 equal to 0, which gives us K to be 2. So we get K to be 2 right there. So when we then say CAB, therefore, it is going to be the matrix C, which is minus 2, minus 1, 1, 1, 1, 3, and the matrix A, which is 1, and in place of K, we put 2, so 1, 2, 3, 2, 1, 3, 3, 2, 5, and the matrix B, 0, minus 2, minus 1, 3, 0, 0. So these are the three matrices we are multiplying. I'll take the first matrix as it is, minus 2, minus 1, 1, 1, 1, 3, and I'll multiply these two matrices. This row and this column, we get 0 minus 2 plus 0. So we get minus 2. Next up, this row and this column, all right, that will give us minus 2 plus 6 plus 0. So minus 2 plus 6 is 4. So we have 4 here. Next up, we will do this row and this column, all right. So that's going to be 0 minus 1 plus 0. So minus 1. Next up, we will do this row by this column, all right, and we will get minus 4 plus 3 plus 0. So minus 4 plus 3 is minus 1. Next up, we will do this row by this column. So that's going to be 0 minus 2 plus 0. So minus 2 here. And lastly, we will do this row by this column, and we will get minus 6 plus 6 plus 0. So we just get 0. Next, we multiply this 2. I'll do this row by this column, and from this we will get 4 plus 1 minus 2. So we get a 3. Then this row by this column, that will be minus 8 plus 1 plus 0, which is minus 7. Then I'll do this row by this column, and I'll get minus 2 minus 1 minus 6. So minus 2 minus 1 minus 6 is minus 9. So minus 9. Lastly, this row by this column, right? And when we do, we get 4 minus 1 plus 0, which is just 3. This is what we're getting. And 3 minus 7 minus 9, 3 is the same here. So we have done it. So I'll say here, shown, like this. Let's move on to part B. It says, find the equations of the invariant lines through the origin of the transformation in the xy plane represented by CAB. Alright, so CAB is the transforming matrix, and it is this matrix that we got above. So basically 3 minus 7 minus 9, 3, multiplying a set of points, giving us an image like this. Multiplying, right? If we do this row and this column, we get 3x minus 7y equal to big X, right? Then when we do this row times this column, then we will get minus 9x plus 3y equals to big Y. All right, so that's what we are having right here. Okay, now we are saying that since we are talking about the invariant lines on the object pass through the origin, okay, then it means that they take the form y is equal to mx, which means for small y we are going to substitute that by mx in the equations above. This is equation 1, this is equation 2. So equation 1 will be 3x minus 7mx is equal to big X, minus 9x plus 3mx is equal to big Y. That's for equation 2. Also, since the image will also pass through the origin, because the lines are invariant, then it means the image will also take the form y is equal to mx. So that being said, we will say big Y is minus 9x plus 3mx should be equal to m of big X, 3x minus 7mx. So minus 9x plus 3mx is equal to 3mx minus 7m squared x. Now all the terms are divisible by x. So we have 9 minus 9 plus 3m is equal to 3m minus 7m squared. Okay, I'm also noticing that these terms are common for both sides, so they get eliminated. So we are remaining with minus 9 minus 7m squared. All right. And if we take everything to one side, we'll be having 7m squared minus 9 equal to 0. So m squared is equal to 9 over 7, which means that m will be equal to the square root of 9 over 7, which is like 3 over root 7, plus or minus, right? So therefore, the invariant lines, which take the form y is equal to mx, will be y is equal to minus 3 over root 7 of x, and y is equal to 3 over root 7 of x. So these are the answers right here. Let's go on to part C. On C, the question says, matrices D, E, and F represent geometrical transformations in the xy plane. So D represents an enlargement, center the origin. E represents a stretch, parallel to the x-axis, and F represents a reflection in the line y is equal to x. Right? So they say, given that CAB is equal to D minus 9EF, find D, E, and F. All right. So they're saying that CAB is equal to D minus 9EF. Now CAB, we got it above to be the matrix 3 minus 7 minus 9, 3. Okay. So 3 minus 7 minus 9, 3. All right. Is equal to D minus 9EF. Now D, that's an enlargement, center origin. The matrix representing that is K0, 0K. You should know. It's minus 9. E is represented by a stretch parallel to the x-axis. And the matrix for a stretch parallel to the x-axis, okay, is stretch vector, say H, 0, 0, 1. And the matrix representing, that's F, a reflection in the line y is equal to x, is the matrix 0, 1, 1, 0. So this is what we need to simplify. So on the right side, we'll be having K0, 0K minus 9 of, and multiplying these two brackets, this row by this column, we get 0, 0, 0, everything. Then this row by this column, second column, we get K, actually H, this is supposed to be H. Then this by this, we get 0, that's 1. And this row by this column, we get 0, 0, 0, 0 here. So we are saying 3 minus 7 minus 9, 3 is equal to K0, 0K minus, and taking the 9 into the bracket, 0, 9H, 9, and 0 here. All right. Which is the same as K minus 0, that's K. 0 minus 9, that's minus 9H. And 0 minus 9, minus 9, and K here. All right. So we can say that this element, first element, is equal to this one here, which means to us that K is 3. And we can also say this is equal to this. All right. Which means to us that minus 9H is equal to minus 7. So H is equal to 7 over 9. Therefore, the matrices will be, let's start with D. Therefore, D, which was K0, remember D was K0, 0K, but in place of K, we're going to put 3. So this is matrix D. Matrix E was the stretch. Remember, it was H0, 0, 1. But in place of H, we're going to put 7 over 9. So we have 7 over 9 here. So that's it. Then for the last one, F, it's still 0, 1, 1, 0, like this. So these are the three matrices D, E, and F they want us to find. Moving on to number 6. On part A, they say, show that the curve with Cartesian equation x minus a half squared plus y squared equals to a quarter has polar equation r is equal to cos theta. Alright. Okay, so we have x minus a half squared plus y squared equals to a quarter. Alright, expanding the brackets, we get x squared minus x plus a quarter plus y squared equals to a quarter. Rearranging, we have x squared plus y squared, right, minus x equal to 0, because we can subtract a quarter from both sides and we'll be good. But x squared plus y squared is r squared, and x is r cos theta. Okay, so we are saying that r of r minus cos theta equal to 0, and r is 0 or r minus cos theta is 0, which is r is equal to cos theta. So this is the result, because r cannot be equal to 0. So this is what they want, and I'll say here shown. That's how we do it for 6 part A. On the next part, they say the curves C1 and C2 have polar equations r is equal to cos theta and r is equal to sine 2 theta, respectively, where theta ranges between 0 and a half pi. The curves C1 and C2 intersect at the pole and at another point P. So on part B, find the polar coordinates of P. Alright. Alright, so we're saying here, since these two curves are intersecting, we can solve them simultaneously, where we can say that cos theta is equal to sine 2 theta, which is the same as saying cos theta minus sine 2 theta equal to 0, which is the same as saying cos theta minus 2 sine theta cos theta equal to 0, and we can factor out cos theta to get 1 minus 2 sine theta equal to 0. So essentially here we are saying that it's either cos theta equal to 0 or 1 minus 2 sine theta equal to 0, which basically is sine theta is equal to a half. So let me just write that as sine theta is equal to a half, which leads us to having theta being equal to arc sine of a half, which is pi over 6. Therefore, when theta is pi over 6, cos of pi over 6 is root 3 over 2. So the coordinates will be root 3 over 2 for r, and for theta, pi over 6. So these are the coordinates of P. Alright. Cos theta cannot be equal to 0 because r is cos theta and r cannot be 0. So here we have no result. So the only one we will get is this one here. These are the coordinates of P. Let's move on to part C. In a single diagram, sketch C1 and C2, clearly identifying each curve and mark the point P. Alright, so to make the sketch, we are going to start with the curve r is equal to cos theta, and I'll make a table of values for it. So I'm going to use these intervals. So when theta is 0, r will be 1. When theta is a sixth pi, r is 0.87. When theta is a third pi, r will be 0.5. And when theta is a half pi, r will be 0. So these are the points, and we can therefore plot them on this graph to get a curve like this one. Next up, we make a table of values for r is equal to sine 2 theta, and when theta is 0, r will be 0. When theta is a sixth pi, r will be 0.87. When theta is a third pi, r will be 0.87, and when theta is half pi, r will be 0. So we can plot these points on the graph again, and we get this curve here. So these are the two curves we get, and they intersect at this point, which is the point P. So I'm going to put the sketch right here. So we have this line, which is the initial line, okay? So theta is equal to 0. And we also have the vertical line, which is the line. Theta is equal to a half pi, all right? So for the curve C1, we saw that it is like this. And for C2, it goes like this. So these are the two graphs that we have drawn. Now, this point here, okay, the point right here is the point P, okay, where the two curves intersect, and this is C1 and this is C2. So this is what we are having here. Let's move on. Now on part D, the question says the region R is enclosed by C1 and C2 and includes the line OP. Find in exact form the area of R. All right. So in this particular case, we are looking for the region which is bound by C1 and C2 and includes OP. This is O right here. Okay. So the region that they want us to find is this region here. That's the region whose area we need to find. Now we know that if I draw a line that passes through P from O, this line is the line theta is equal to a sixth pi or pi over 6, because that's what we got right on part B right here. Okay. So to get the required area, we can start by finding the area, which is this area here, okay, which is the area that is enclosed by C2 between theta is equal to 0 and a sixth pi. All right. So for the little area that I've shaded right here, we are going to use the fact that area is found by the integral from alpha to beta of half r squared with respect to theta. So therefore, for the required area, the shaded area, we will be saying that it is equal to half integral from 0 to a sixth pi, that's pi over 6, of, since we're talking about C2, C2 has the equation r is equal to sine 2 theta, all right? So this will be sine squared 2 theta with respect to theta, okay? And we're going to add that to the area which is above, okay, which is this other area here. And this other area is bound by the curve C1 within the region pi over 6 to pi over 2, okay? So I'm going to say here is plus the integral from a sixth pi, that's pi over 6, to half pi, which is pi over 2, okay? And I'll factor out the half, okay? So I'll have the half outside like I did here, and here we know that the equation of the curve is r is equal to cos theta, so I'll say here cos squared theta with respect to theta. So this is what we are working with, all right? So let's use this for finding the required area, okay? So this should be equal to half, and integrating sine squared theta and cos squared theta, we are going to use these identities here, all right? So that means when integrating sine squared theta it's like integrating from 0 to pi over 6 half of 1 minus cos 4 theta with respect to theta, and that's plus half of the integral of, for cos squared theta, using one of the identities, we get from the limits are pi over 6 to pi over 2, so that's half of 1 plus cos 2 theta with respect to theta. So essentially we have a quarter of the integral from 0 to pi over 6 of 1 minus cos 4 theta with respect to theta, and that's plus a quarter of the integral from pi over 6 to pi over 2 of 1 plus cos 2 theta with respect to theta. All right, so now this is a quarter of, and integrating 1 minus cos 4 theta, we get theta minus a quarter sine of 4 theta here, and it's with the limits 0 to pi over 6, and it's plus a quarter of, okay, integrating 1 plus cos 2 theta, we get theta plus half sine 2 theta. The limits are still pi over 6 and pi over 2. All right, so this is going to be a quarter of, and substituting pi over 6 into this, we get pi over 6 minus, and here we have a quarter of sine of 4 of pi over 6, which is sine of 2/3 pi, which actually is root 3 over 2. Okay, and it's going to be minus. Now we substitute 0 into this thing, and it will give us 0. So it's plus a quarter. Coming to this other part, substituting pi over 2, we'll be having pi over 2 plus, here is half of sine of 2 of pi over 2, which is sine pi, and sine pi is 0. So we get 0, and it's minus. Substituting pi over 6, we'll be having pi over 6, and it's minus half of, and sine of 2 of pi over 6 is sine of 1/3 pi, which will give us again root 3 over 2. So this is what we have, and we need to simplify this. Okay, so we have here a quarter, multiplying it into the bracket, we get pi over 24, and multiplying here we get minus of root 3 over 32. All right, and here I'm going to multiply a quarter times this, and we are going to get pi over 8, and a quarter times this, we get minus pi over 24, and a quarter times this, we get, that's minus root 3 over 16. All right, so this will give us, I think you can see that these two terms will give us 0 when they add up. Okay, and minus root 3 over 32 minus root 3 over 16 should give us minus 3 root 3 over 32. All right, so we have minus 3 root 3 over 32. Okay, minus here, and we still have the pi over 8 over here, and we can simplify this by factoring out an eighth, so that we have pi minus 3 root 3 over 4 inside the bracket, and this here is the answer, and that's how we do it right here. Let's go on to the last question on this paper, and that's number 7. It says the curve C has equation y is equal to f of x, where f of x is equal to x squared plus 2 over x squared minus x minus 2. So on part A, find the equations of the asymptotes of C. Let's start with the vertical asymptote, and we get that when we equate the denominator to 0, so x squared minus x minus 2 equal to 0, right, which is x minus 2, x plus 1 when factorized. Therefore, x is equal to 2 and x is equal to minus 1 are the vertical asymptotes. Next up, we can see that we actually have a horizontal asymptote, and we can get that by dividing the coefficients of the leading terms, which is 1 over 1 in this particular case. So basically it's y is equal to 1. So that's what we have for the asymptotes. Okay, this is the horizontal asymptote. Let's go on to part B. Find the coordinates of any stationary points on C, giving your answer correct to 1 decimal place. Stationary points on C. Right. So we have the equation here. F of x is equal to x squared plus 2 over x squared minus x minus 2. Right. So we are saying since f of x is equal to x squared plus 2 over x squared minus x minus 2, at stationary point f prime of x will be equal to 0, which therefore means that if we find f prime of x, which is x squared minus x minus 2 times the derivative with respect to x of x squared plus 2 minus x squared plus 2 times the derivative with respect to x of x squared minus x minus 2 all over x squared minus x minus 2 squared. This whole thing should be equal to 0. Okay, so we will be having differentiating here. We get 2x of x squared minus x minus 2, and it's minus x squared plus 2 of differentiating this, we get 2x minus 1, right? So all this is equal to 0 because when we multiply both sides by the denominator, we get 0. So 2x cubed minus 2x squared minus 4x minus here, that's 2x cubed plus 4x minus x squared minus 2 equal to 0. So we have 2x cubed minus 2x squared minus 4x minus 2x cubed minus 4x plus x squared plus 2 equal to 0. Alright, now these will give us 0 when we add them up. Minus 2x squared plus x squared will give us minus x squared. Minus 4x minus 4x is minus 8x, so minus 8x here, and the plus 2 is there, this one, equal to 0. Alright, so basically this can be expressed as x squared plus 8x minus 2 equal to 0, which we can solve quadratically using the quadratic formula, right? So if you use the quadratic formula here, you are going to have x to be minus 8 plus or minus the square root of 8 squared minus 4 of 1 of minus 2 all over 2 of 1, and you will get minus 4 plus or minus 3 root 2 as a result. So minus 4 plus or minus the square root of 3 root 2. For these values we have gotten, we're going to have a little table of values, x, y. So we have minus 4 minus 3 root 2 and minus 4 plus 3 root 2. So we are going to substitute them into the original function, and when we do, we will get y coming out as 0.9, and that is to 1 decimal place as they want here. And when we substitute minus 4 plus 3 root 2 for x into the function, we get minus 0.9. Now, minus 4 minus 3 root 2 itself is actually minus 8.2 to 1 decimal place, and minus 4 plus 3 root 2 to 1 decimal place is 0.2. So the coordinates we have are minus 8.2 and 0.9, and 0.2 and minus 0.9. So these are the coordinates we're looking for. Let's move on to part C. On C, it says sketch C, stating the coordinates of any intersection with the x's. Alright, so to sketch the curve, we are sketching the curve for f of x is equal to x squared plus 2 over x squared minus x minus 2. Alright, so I'll have the two x's, x and y, and the origin is here. We are considering here that we have asymptotes at x is equal to minus 1, this one here, and at x is equal to 2, this one here. And we also had on part A the horizontal asymptote at y equals to 1, which is this line here. So next, we will look at the behavior of the graph about the asymptotes. Right, so about the vertical asymptotes, starting with the asymptote x is equal to minus 1, I'll take a value that is slightly less than minus 1, which is minus 1.01, and a value that is slightly greater than minus 1, which is minus 0.999. So for these two values, when x is equal to minus 1.011, you will get that y comes out as approximately 1000, which is a very high y value, so we know that our graph will be coming from up here. And when x is minus 0.999, we get a very low value, which is approximately minus 1000, which means the y value will be slightly down here. For the asymptote x is equal to 2, we'll consider a value that is slightly less than 2, which is 1.999, and slightly greater than 2, 2.001. When x is 1.999, y is approximately minus 1999, which means it's coming from down here. And when x is 2.001, y is approximately equal to 2000, which is a very high y value, so the graph will be coming from up here. Now, considering the behavior of our graph as x approaches positive infinity, I will take a very large value of x, like x is equal to 1000, and substituting it into the equation, we get a corresponding y value of 1.001, which means that as x becomes large, it will be approaching the graph from slightly above y is equal to 1. So 1.001 is slightly above 1, so somewhere here. As x approaches negative infinity, I'll take a very small value of x, like minus 1000, and substituting it into the equation, we get an output of 0.999, which means that the graph is slightly less than 1 at 0.999, which means it will be approaching from slightly below, right here. We're also considering that on part B, we worked out the coordinates of the stationary points to be at minus 8.2 and 0.9 and 0.2 and minus 0.9. So we know that this graph will have a couple of stationary points. So eventually, with these markers, we will have our curve like this. We have the y-axis, the x-axis, the asymptote here at minus 1, and another asymptote at 2. And we have a horizontal asymptote at 1. So it intercepts at 1. And our graph came out like this. And we also had this. And here it came down and like this. So this is what we get for this particular graph. Now the question also says we should state the coordinates of any intersections with the axis. So you can see here that the only intersection of this graph with the axis is here, where the graph intercepts the y-axis. Now we know that when the graph intercepts the y-axis, it will be at a point where x is 0, right? And if we go to the original function, when x is 0, you will get that we get y to be 2 over minus 2, which is minus 1. So the y coordinate is minus 1. So the coordinates of this particular point should be 0 and minus 1. So this is what they want us to do for this particular graph. On part D, the question says we should sketch the curve with equation y is equal to 1 over f of x. Now here we are talking about a reciprocal graph. So if we take the original graph for y is equal to f of x, we can make use of this graph of y is equal to f of x to find the reciprocal graph. Starting with the asymptotes, we know that for the reciprocal graph, the horizontal asymptote will remain. As for the vertical asymptotes, they will become intercepts of the reciprocal graph, so we need these 2 points. Also considering the stationary points, we know that where the graph of y is equal to f of x has a minimum, it will become a maximum for the reciprocal graph. So we can put a maximum point here. And where the original graph was maximum, the reciprocal graph will have a minimum. So I'll also mark this point here as a turning point. Also, you need to understand that for the graph of a function and its reciprocal, they will always intercept at y is equal to 1 and at y is equal to minus 1, which is at these 2 points here. And lastly, it's important for you to know that as f of x increases, the reciprocal graph decreases and vice versa. Okay, so to make the sketch, it should now come out like this all the way. So that is the reciprocal graph that we'll be having. So I'm going to make a sketch of it right here. So I have the axis, and we also have the horizontal asymptote, and it intercepts the y-axis at 1. Remember, this is the y-axis and this is the x-axis, and we say that the reciprocal graph will come down like this, and it will be like this. All right, so important points are this point here is still the point 0 and minus 1, and this intercept, which was once a vertical asymptote for the original graph, is at minus 1, and this one is at 2. So this is the graph we get. Let's move on. On part E, they say find the set of values for which the reciprocal graph is less than the graph of the function f of x. Right, so if we go back to the graphs, here I have the 2 graphs superimposed. The red one is the graph of y is equal to f of x, and the one in black is the reciprocal graph. Now, in order for us to solve the inequality 1 over f of x is less than f of x, we have to first figure out what the intercepts between the 2 graphs are, especially the x values of those intercepts. So remember, we say the 2 graphs intercept where y is equal to 1 and where y is equal to minus 1. So let's start with where y is equal to 1. So I'm going to take the original function, which is y is equal to x squared plus 2, and that's over x squared minus x minus 2, and I'll equate that to 1. Multiplying both sides by the denominator, we get x squared plus 2 is equal to x squared minus x minus 2. Subtract x squared from both sides, we get 0, and moving everything to one side, we'll be having x plus 4 equal to 0, such that x will be minus 4. So this is the x value at this particular point. We also need to find the other intercepts right here, and this is where the graphs intercept where y is equal to minus 1. So basically, we are saying that x squared plus 2 over x squared minus x minus 2 is equal to minus 1. And multiply both sides by the denominator, we get x squared plus 2 is equal to minus x squared plus x plus 2. And if we move everything to the left side, we'll be having 2x squared minus x, and 2 minus 2 is 0. So all this is equal to 0. Factor out x, and we'll be having 2x minus 1 is equal to 0, such that x is equal to 0 or x is equal to a half. Alright, so we have 0 and a half being the x values for these 2 points. Alright, so remember, we're looking for the set of values for which the graph of y is equal to 1 over f of x, which is the reciprocal graph, is less than f of x. In other words, where the graph in black is vertically below the graph in red. So I think you can see here that for this region, which is between -4 and 1, the graph in black is vertically below the graph in red. So that's a solution, okay? So I'm going to write that down. That's -4 is less than x, and x is less than -1. All right. If we go back to the graphs, you can also see that for the region from here to here, the reciprocal graph in black is vertically below the graph in red. So that's again a solution. That's between 0 and a half, remember? So again, 0 to a half. Lastly, if you look at the values that are greater than 2, you can also see that the reciprocal graph is vertically below the graph in red. So again, for values of x that are greater than 2. So what we have here is the solution.